to speak, and I think I have to hit continue here.
Yes.
And thank you for everybody who's joining us today. I'm not going to assume, I'm looking at the list of participants. I'm not going to assume that anybody knows what a matroid is, but I'm going to assume some graph theory familiarity. There are some people that I don't recognize on the list. There's some people that I do who are going to already have all the background from matroid theory. But if I say something that you would like an explanation for, then please interrupt. It won't be a problem at all. I'm going to explain what a binary matroid is. So today I'm going to discuss some joint work with James Oxley and Chris Wetzler. I'm currently at the United States Naval Academy, and I've been here since January 2016. This work, I decided to talk about it because it's a project that gives me the opportunity to introduce matroids that are close to graphs. So they're kind of friendlier, they're more manageable than matroids in general. And it's a project with James Oxley. He's one of my favorite matroid theorists. And Chris Wetzler, she's another discrete matroid theorist. So it's kind of, I wouldn't call it a boutique result. It's a nice result and it's well motivated. And it may seem somewhat random to say, okay, we're gonna say all of our odd circuits have size 3 or 5, but hopefully I'll convince you that it's an interesting set of matroids to look at by the end of the class, by the end of the seminar. What is a matroid? Instead of saying the definition and then giving examples, I'm going to give an example and then say the definition. In space, you can have points, and those points, when a matroid theorist looks at points, we don't care what the coordinates are. We just care about the relationships between the points. So I don't care about the XY positions of these points. If you translate them up or down or left or right, if you stretch them, compress them, whatever, I don't care what you do to them. As long as the relationships remain intact, the matroid looks the same to me. So the matroid it consists of the points, which are the ground set, and then collections of those ground set that we call independent sets. An independent set is going to be a set of elements that don't depend on each other. What does that mean? Here I have 3 elements in green. 3 points define a plane. If I add a 4th point to that set, that 4th point, in order to be in the plane, it has to depend on the other 3. So that's a dependent set. That 4th point depends on the other points. So James Oxley likes to say, and I really like this analogy, a 3-legged stool never wobbles. A 3-legged stool never wobbles because 3 points define a plane. As soon as you introduce a 4th leg, if the length of that 4th leg does not depend on the other 3, then you could have a wobble because it could define multiple planes. So if I have a 4-point dependent set, it could look like this 3-element set. I mean, this red set. But if I want to have a 3-element dependent set, what do you think that should look like? There are 3-element dependent set here.
Like on one line, like the
exactly
across.
Yeah. A 3-point collinear set, that's dependent because the 3rd point depends on the other point. And I threw another one in there. So there's 2 3-element dependent sets. Every other 3-element set is independent. So these independent sets, let me also mention a minimum sized dependent set, such as this set of red points, we call that a circuit. So if I just look at any proper subset within that red set, what I get is an independent set. So this is a minimal, not necessarily minimum, well, in this case, minimum, but this is a minimal dependent set. So it's a circuit. So independent sets, they obey 3 axioms. And 99.9% of matroid talks that I've ever seen include these axioms pretty much up front. And I've sort of buried them a little bit. I'll show them to you in a second. But the empty set has to be independent. The second axiom is that a subset of an independent set is also independent. And both of those make sense. And if you think about it in terms of linear algebra, which we'll get into in a second, you can think about linearly independent sets of vectors. That's going to work for those two. And the third axiom is where all the money is. If I have 2 independent sets where one is larger than the other, then there's an element in the larger one I can add to the smaller one, an element that's not in the smaller one yet. So an element in the bigger one that's not in the smaller one that I can add to the smaller one to get a new independent set. So if I take these 3 blue points and I take a smaller independent set, okay, it would have to be at most 2 points. That smaller independent set really only defines a line. So there's going to be some element in that this 3 element set that is not on that line. So adding that to the other 2 points, I would get an independent set. So that makes sense, hopefully, in some way. Even if these 3 axioms are a little bit weird to look at, in terms of geometry and thinking about points in space, it can make sense. And we're not limited to a plane. We're not limited to any dimension. And actually, we're not even limited to Euclidean geometry, but I won't get into that right now. I want to talk about matroid theory coming out of the work of Whitney. So Hassler-Whitney and Takeo Nakasawa independently came up with the notions of matroids. And there were some other people who were studying similar notions around that time. So I want to attribute it to both of them, and probably the list should be longer. So they looked at notions of independence in mathematical objects. So I've told you what a matroid is when we think about it as points in space. So how do you think we can get a matroid from a graph? What would our independent sets be? And I want to, as a clue, I'm going to say, if you know what an independent set is in a graph, then that might actually hurt you in trying to figure out what an independent set should be to get independent sets for a matroid based on a graph.
I'm guessing that like 2 points in the graph is independent if and only if they are non-adjacent, right?
That's because you know graph theory.
Okay.
I tried to warn you. I tried to warn you. So it turns out that that's not the notion of independence that I'm looking for. So I want my ground set. Well, here's another clue. So I want my ground set to be the edges. And remember that a dependent set has a circuit is a dependent set. So what type of sets do we want for our independent sets in a graph if our edges are the ground set to get a matroid?
Maybe like forests or something.
Yeah, that's exactly it.
And Rex also saying it.
Yeah. So edge sets of forests. Every set of edges that does not contain a circuit is going to, well, so every edge set that doesn't contain a cycle, if you take those to be your independent sets, it will obey all of these axioms. For 1 and 2, it's straightforward. 3 is a nice exercise to give undergraduates. And now I'm going to put up the incidence matrix of this graph. So my columns are labeled by the edges, my rows are labeled by the vertices, and I've got 1s whenever the vertex and edge are incident. And the independent sets that I get here, well, so here I've got a matrix over the 2-element field. So 1 + 1 = 0 in this field. So I can see that 1, 2, 3, when I add these vectors together, I get the 0 vector. So this is a dependent set, a linearly dependent set. And we can see that corresponds to 1, 2, 3, the cycle in the graph. So instead of calling it a cycle here and a linearly dependent set here, let's just call it the circuit of a matroid. So every graph is a matrix. Every matrix is a matroid, and these are all proper containment. So I would never do this, but I do know of a matroid theorist who refers to graph theory as degenerate matroid theory. I would never do that, but and I won't admit who it was, but at least one of the people on this in the audience here knows who it is, I think. So the Venn diagram of this is just a bullseye. You have graphic matroids, matroids that are representable by matrices over the 2-element field, which we call binary matroids, and then all matroids. But actually, every circle should be like infinitesimally small because the number of matroids that are graphs compared with all matroids, they're vanishing. They have, if you take the n-element graphs divided by the n-element matroids, take that ratio as n goes to infinity, it goes to 0. So graphs are a vanishingly small set compared with matroids. And these two matroids are the same. So the matroid you get from the graph, we call it M of G. The matroid you get from the matrix, you call it M of A, and they're the same. So I've just told you what a binary matroid is. It's any matroid that has a representation like this. And that bullseye tells us, okay, all matroids, that's a really interesting and rich group of things to think about, but binary matroids are properly contained in that, and they properly contain graphs. So this is a really nice class of objects, and it's a natural thing to do to try, if I've got a graph result, and I think this is something that's going to work for matroids, I'll start with binary matroids. That's a really common technique in matroid theory. Minors are something else that I need to mention. So here's some things you can do in a graph. You can delete an edge. Here I've deleted 3. You could contract an edge. I contracted 1 here. You can do a sequence of these and you get minors. Please stop me if I'm about to skip this slide now. Does anybody need clarification on that? So matroids behave in the same way. I should mention that. Deletion, if you think about a matrix, a binary matroid, deletion is removing a column. Contraction is doing a pivot on a column and then removing a row and a column. So contraction brings down the rank, just like contraction here brings down the size of your largest spanning tree by 1 edge. Characterizing a class by its forbidden structures is it's a classic, oh, it has the word class in it. It's a classic strategy. It's classification is the classic strategy. Kuratowski / Wagner, is it Wagner or Wagner? It's probably Wagner. They proved that a graph containing, essentially, they both proved that a graph containing no K5 minor or K3 minor is planar. So this tells us that we can embed the graph in the plane exactly when it contains none of these excluded minors. Cool. And Robertson and Seymour did this really big project called the Graph Minors Project that told us it's really important, like these excluded minors are really important because actually every surface can be characterized by its excluded minors, and these excluded minors are a finite set. And that's really cool. They didn't tell us what the minors are for other surfaces, but they told us there are a series of papers. It was a project that lasted over 20 years, and there were a couple dozen publications in the top journals. And other people worked on this project as well. Thomas worked on this project. Judnowski may have contributed to it. So that's a really beautiful result in graph theory. And I love being able to mention it in my talks. So this is a little bit, it's somewhat related. It's related enough that I can mention it. And Tut proved that we can characterize binary matroids, which another way of saying that is a matroid representable over GF2, the two-element field, by just avoiding one excluded minor. It's U2-4. So this is, if you're thinking about it geometrically, it's 4 points on a line. So that would have rank 2, meaning the biggest independent set is 2 elements, and it has 4 elements. The U is for uniform. So every set, if I have 4 elements, every set of up to 2, of size up to 2 is independent. Every set with more than 2 elements is dependent. That's what this U2-4 tells me. I just have, yes?
I have one question. So do you have an easy explanation if a matrix contains U2-4, then it cannot be represented over F2? Do you have an easy explanation to that?
Yes.
Okay.
I haven't written it down, so I'm going to try to explain it verbally. Otherwise, I have to get my phone on the call and then use it as a webcam. But what you can do is, wait, I can give you an easy explanation for why U2-4 is not representable over the binary field. Is that?
Sure, that is what I'm asking, yeah.
Okay, so we can say, okay, maybe it is representable. Then we can represent it with a matrix, and our matrix, because this is a rank 2 object, we only need 2 rows, and we're going to have 4 columns. So once we have 2 rows and 4 columns for our elements, then we run out of columns that we can use, right? We can have 1, 0, 0, 1, 1, 1. If we have a 0, 0 column, that actually would be a loop. And then you can't include that loop in any basis, in any independent set. But U2-4, every pair of elements is an independent set. So they all have to be non-zero vectors, but you have 1, 0, 0, 1, and then 1, 1, and then you have to repeat something. Whatever you repeat, put it with its copy, and that's a dependent set of size 2, which you're not allowed to have in U2-4.
Yeah, got that. So you run out of the like labels to represent elements. Yeah.
U2-4 is representable over every field that has enough elements, basically. Yeah, any other questions? That was a good question. I like it because I could answer it. All right, so I told you 1 excluded minor result in graphs, and I told you that's just one example of an infinite series of excluded minors that minor characterizations that could exist as soon as we start characterizing all the excluded minors for these other surfaces. Well, this example by Tut, it's one of many possible characterizations that can be done. You can take any finite field, and it turns out the matroids representable over that field are characterized by a finite set of excluded minors. So I think that's cool. And it's because this conjecture of Rhoda was resolved by the Matroid Minors project, which has been done. It's still being done, being written up by Jeff Whittle, Jim Geelan, and Bert Herards. So I love talking about these results because they are super, super cool and powerful and deep. And now I'll talk about, okay, so if I want to take a set and then say what are its excluded minors, that's a natural question. What if I start with an excluded minor and then see what class of things I get? There are some really clever people interested in questions like that. And so whenever I have a question that I'm trying to answer, I'm always encouraged by people that I know are clever, who are interested in similar things. So this is a claw graph. It's got 3 edges incident with a vertex, and then 3 non-edges around the neighbors. So it's a K13 where the induced subgraph on those 4 vertices is a K13. So these the dashed lines are non-edges. So if you forbid this claw graph, whether you care about a claw graph or not, it's objectively worth looking at because Maria Chudnovsky looked at it, right? So Maria Chudnovsky and Seymour gave a complete structure theory for the class of claw-free graphs. And there was other work done on the class of claw-free graphs that showed that they're really useful, and they're a really useful class of graphs that are they're useful because of their polynomial time algorithms, and they're sort of tractable. They're a set of graphs that are tractable. So you can characterize a class with exclude minors. You can start with a minor, try excluding it. These are all questions that matroid theorists and graph theorists love. So avoiding odd circuits. We know how to do that in graphs. If we want to avoid all odd circuits, a graph contains no odd cycles if and only if it is, yeah, I saw Shujing say it is bipartite. Yes. A binary matroid, it turns out it has no odd circuits if and only if it is affine. We call it affine. So if you want to think about just the graph theoretic part of this talk, then every time I say affine, you can think of bipartite. The last piece of terminology I need to define is connectivity. I'll say something about duals, but I'll probably skip through that fairly quickly. So connectivity, when is a graph connected? A graph is connected when it's not disconnected, right? So if it's not in 2 pieces, then the graph is connected. When is a graph not 2 connected? Well, it's not 2 connected when you can find a vertex that the graph breaks apart across. So this is like a direct sum. So this graph on the right, it's not TUT2 connected. So we're talking about TUT connectivity. When is a graph not 3 connected? Or when is a graph 3 connected? A graph is 3 connected when it doesn't fail to be 3 connected. Here's how it could fail. I could have a 2-sum. So to do a 2-sum, you identify 2 edges in a graph, you glue that graph together, those 2 pieces together across that edge, and then remove that edge. If a graph can be built in that way, then it's not 3 connected. So the graph on the right-hand side is not 3 connected. Matroid theorists think of connectivity, disconnectivity, and 2 connectivity exactly the same way. We don't actually recognize this when something is has a cut vertex, that to us would still appear disconnected. And you can think about, okay, building a spanning tree in this right-hand graph, because those would be bases for your matroid. That would be the same thing as taking a basis of this right-hand part, union the basis of this part, and that's exactly how you get all the bases. So whether those pieces are together or apart, I nearly said together or apart, a matroid theorist doesn't know. So we say either something is, when we say something is connected, we mean 2 connected, because this really, the bases of the right-hand graph, it's not just the union of a basis with the left with the basis of the right, because that would give you some overlapping span of these 2 vertices. So there's a relationship there, but it's not the same thing as being disconnected. And just to prevent you from thinking, oh, well, there are no 3 connected graphs. I have a way of doing it as a 2-sum, where I just take a parallel pair and then 2-sum that onto a graph. So there are no 3 connected graphs. So just to be pedantic, I'm going to mention every side has to have at least 3 elements or 3 edges. So connectivity, we're going to talk about it in terms of graph, but it works the same way in terms of matroids. A matroid is connected when it's hard to break apart in a sense. Maffray has a theorem from 1992. We know about avoiding all odd cycles. What if you allow triangles, but no other odd cycles? Well, it turns out then either you've avoided all odd cycles, so you're bipartite, or your graph is not big enough, so it's got at most 4 vertices. So it can't have a 5 cycle because it doesn't have 5 vertices, or it looks like this. So this is a nice characterization because it's very explicit. And it's very natural to think, okay, well, what happens when we look at binary matroids? I know what a 2-connected binary matroid is. I know it's circle. I could just think instead of odd cycles, avoiding odd circuits. Well, instead of bipartite, you'd have to use the word affine. Instead of K4, it turns out that, so for K4, you have 4 vertices in every possible edge. But as soon as you take the geometric representation of that in binary space, or take the binary matrix representation of K4, it turns out there's 1 more column that you can add. And when you add that 1 more column, what you get is the phonomatroid called F7. So number 2 has to change to K4 or F7, the phonomatroid. And number 3 actually just stays intact. So Oxley and Wetzler, my co-authors, so this is not with me, they proved in 2016 that all odd circuits in a connected, and I'm just going to slip the word simple in there for technical reasons, binary matroid have size 3 if and only if it is affine, it's not big enough to have a 5 circuit, or it's the matroid of this graph. So I really think this is a beautiful result because it goes straight from graphs to matroids. So that shows us that really wasn't a graph result. It was a binary matroid result in disguise. It was a special case of a binary matroid result. So I really like that. One
question. So does the phonomatroid have something to do with the phonoplane?
It is the phonoplane, yes.
It is, okay, thanks.
That's it, yep, exactly. So what you do is you take a binary matrix with 3 rows and every possible column other than the 0 vector. And you get, so yeah, the binary projective plane, the phonoplane, the phonomatroid. Yeah. Yeah, good point. There's a lot of things that go by several names. So yeah. I'm going to skip through this part about the dual, just for the interest of time, but I'll leave it in the slides in case somebody wants to look at the slides later on. Another way to state this result, or a corollary that you can get from this result, is we can guarantee that it's affine if we avoid the 2 conditions that are not affine. So if we say, well, we're looking at a cosimple connected binary matroid with rank at least 4, so it could have a 5 cycle, like it's big enough. So it's got rank at least 4. Then all odd circuits have size 3 if and only if M is affine. So that's like, okay, there's these things that you can get, but this graph on the bottom here, this is not cosimple because it's got these series pairs. We call them series pairs, I think, in matroid theory and graph theory, right? Vertices of degree 2. So if I say, well, you're not allowed to have series pairs and you're not allowed to have low rank, but you can have triangles, it turns out you can't have triangles. Another result that Oxley and Wetzler have from 2019 is that when we bump up to allowing 5 edge cycles, we have the same 3 types of conditions. Either it's bipartite, or it's not big enough to have a 7 cycle, or it looks like this. So what you the right way to think about this, just for moving forward in the talk, is like a book. So think about these three vertices as being on the spine of a book, and it's got pages, and each page has a single vertex of degree 3 that's adjacent to the three vertices on the spine. So each page is just a vertex in this K3n, and the book is allowed to have, it has at least one edge on the spine. It can have up to all three edges. It could be a triangle on that spine. So either it's bipartite, it's always allowed to be bipartite. You avoid all odd cycles, or it's not big enough, or it's this book. So here we're talking about three connected simple graphs. We've bumped up the connectivity, we've bumped up the number of edges in odd cycles that we allow. There's another generalization that they do where we bump up the connectivity, we bump up the size of the circuits that cycles that we allow. So I just want to put this here because I think it's really cool. They showed that when you say, okay, we're going to take an n-connected simple graph, and it's allowed to have odd cycles up to size 2n minus 1, but nothing bigger, then either, and it has no larger odd cycle, then either it's not big enough to have a larger odd cycle, or it's a book. I mean, it's a book. Okay, I mean, it's a bipartite graph where you can have a complete, up to a complete graph on the n vertex side. So I really like that because it's exactly, I mean, it's the pattern carrying through like exactly. There's nothing extra that we get. So in order to talk about the binary result, a book of binary pages, you can see, okay, if I fill in these dashed lines, you can see that there's a K4 happening here. This vertex, along with the three vertices on the spine, gives you a K4. And really each of these pages looks like it's got a K4 on it if you fill in that whole triangle in the spine. And we know that with binary matroids, K4 is not the full rank 3 binary thing. So if we're going to switch to looking at the binary case, we have to allow these pages to not just be degree 3 vertices, but to be phonoplanes. So this is my attempt to make a book of phonoplanes. So now I'm going to talk about sort of the graph book and the binary book, and it's two different things. So the points on the top picture are vertices. The points in this bottom picture, these are elements. So this 3 vertex, okay, I said the wrong thing. This 3 element line, those are 3 elements in a dependent set. That's a circuit. These are a circuit. So it's like the triangle here, but these elements are the edges, not the vertices. I know like they look exactly the same. I should probably make them a different color or something. But these elements correspond to edges. And so these pages are phono pages. So Oxley and Wetzler laid all this groundwork, and then I was visiting James, and I wanted to work on some splitter theorem stuff, which we worked on a splitter theorem project that took 10 years, and it left scars. And we got this really beautiful result that I love, and it's powerful, and it was kind of a long time coming. There were sort of partial results in that direction by other groups, even like Jim Geelan had a result in this type. So I was trying to tell him we need to because we got a really technical result. And I said, we need to change this, make it more manageable. And he said, hold on, let's put that on the back burner. I have this project that I want to generalize to binary matroids. We have the graph result. So we worked on this with Chris Wetzler, and we were able to generalize the graph result to binary matroids. And it turns out that it's exactly what you would hope, except for part 4. So ignore part 4 for a second, and we can just bask in how nice that theorem would be if part 4 weren't there. So all odd circuits of a 3-connected binary matroid have size 3 or 5 if and only if it's affine, it's not big enough to have a 7 cycle, so it has rank less than 6, or it has a 3-connected restriction of a book. So 3-connected restriction, I don't need all of the points in each of these pages to stay 3-connected. I do when it's the graph version. You need all those edges. Otherwise, you'd get a series pair or something smaller. But so each of the pages in the binary case can either be a Fano, or you can delete one of these elements, in which case you're left with a K4 sort of hanging off of there, like similar to the degree 3 vertex. So it could be a 3-connected restriction of a book. And if that's where it ended, it would be the exact analog. But it's not really so much different from that, because the only other option is that your binary matroid could have rank 6, and there's only 9 matroids that it could be. So that's a really nice, we would call this ground dwelling junk. That's what Jeff Whittle calls it. He calls it ground dwelling junk. And it doesn't tell you, okay, this is not a true theorem. It tells you there are some sporadic cases, maybe degenerate cases, where this does not, these 3 cases do not hold, but there's only 9 of them. 9 is a finite number. So we still really like this result. And what I put up here are hypergraphs. And I put up hypergraphs because I like them. But these are binary matroids. To interpret any of these, what you can do is, like for this top left one, you take the incidence matrix of it. And then see, I boxed 4 of these vertices because that's not an edge, that's a hyper edge. So you have your incidence matrix of this graph, and then you add a column for this hyper edge incident with these 4 vertices. So you make a column that's incident with those 4 vertices. And that would be a representation, a binary representation of this hypergraph. Some of the hypergraphs have multiple hyper edges, so I went a little bit overboard with presenting these, but you didn't want to see the binary representations. Maybe you didn't want to see the hypergraph representations either, but that happened.
One question is,
yes,
there anything special about those 9 sporadic examples?
That's a good question. They have in common the way that we built them.
Okay.
So the way to build one of these is to start with a 5 cycle and say, okay, we know that the rank has to be higher than 5. I mean, higher than 4, because a 5 cycle only has a spanning tree with 4 edges. So that's rank 4. So my 5 cycle, the rank has to go up at least 2 in order to have a 7 cycle somewhere in it. So I start with my binary matroid that's just got a 5 cycle. And then I add a triad. And how can that triad sort of glue on to it? And then how can that be related to even increasing the rank 1 more time?
I see.
So maybe the short answer should have been no. There's nothing interesting about this.
Just out of curiosity, because when you see sporadic examples from time to time, maybe they have something special inside.
They might have something special. Yeah, it's a fair question. Nothing that I noticed in particular.
I see. Okay.
As a corollary, so I'll get into, if I have time, sort of how we built those and how we proved this. But when should I end this talk?
I think you have 5 to 10 more minutes.
Okay.
Yeah.
All right. So I'll start with this corollary. So because binary matroid, we have the binary matroid result, another common trick to do is to look at regular matroids. I haven't said what those are yet, but a regular matroid is a matroid that has a representation over every field. So every regular matroid is binary. Some binary matroids are not regular. So in the bullseye, we've got graphic matroids. Every graphic matroid is regular, and every regular matroid is binary. So this is a common trick. If you're a matroid theorist, you say, oh, this graph result really points us in the direction of something that's matroidal. I think this is a matroidal property. Let's prove it for matroids. And then we say, oh, we tried to, it's too hard. Okay, well, let's prove it for binary matroids. And then you try to do that and you say, oh, no, that's too hard. Then you try to prove it for regular matroids. And if that is unsuccessful, then you need a new project. But so regular matroids are a really wonderful class of matroids. And they're even closer in some sense to graphs than binary matroids are. So every binary matroid result will have a corollary for regular matroids because they properly contain the set of regular matroids. So it turns out that all odd circuits of a 3-connected regular matroid have size 3 or 5 if and only if. And here my list is exactly the same, except I don't have those 9 sporadic guys, so I don't have number 4 because none of those were regular. And the phonomatroid is not regular. So my books become graph books. These are graph books. So either it's affine, it's too small to have a 7th circuit, excuse me, or it's the cycle matroid that you get from a graph book. So this is really pretty much exactly the graph result. So I really like this one. This is something to do with the dual, and I skipped over it last time. I'm going to skip over it again, but I'll leave it up in the slides in case people are interested. And I'll get into like a small sketch of the proof of the main theorem. So we assume that M is 3 connected and it has a 5 circuit, but no larger odd circuit. That puts a lot of restrictions on how we can build the whole matroid starting from our 5 cycle. If there's no 5 circuits in the matroid, we already know what it is because we have that result where we only allow triangles. So then we say, okay, our matroid has a 5 circuit and it's 3 connected. And then what we would prefer to deal with is something that's minimally 3 connected, meaning that anytime I delete an edge, it's no longer 3 connected. So I want it to be 3 connected, but minimally 3 connected, because there's some nice results about minimally 3 connected things. So we start with our matroid, we remove things staying 3 connected and keeping our 5 circuit until we're minimally 3 connected. It may be that it's not exactly minimally 3 connected, because it may be that, okay, deleting this edge doesn't destroy 3 connectivity, but it does destroy all of my 5 circuits. So in order to preserve a 5 circuit and preserve 3 connectivity, this is what I'm left with. So if the 5 circuit is spanning, then we can find a triad that's disjoint from that circuit. And Menger's theorem tells us, okay, between two subgraph, or let's just say 2 vertices in a 3 connected graph, there's 3 disjoint paths. That's Menger's theorem for graphs. And there's a generalization of that theorem that Tut did to tell us what to do when we're working with matroids. So when I have this 5 circuit and I know I have a triad being, it's similar to a degree 3 vertex. And I know that that exists because I know the rank does go up by 1. Then I can find a relationship between that triad and that 5 circuit. It's glued on to it somehow. And then we use these configurations. For example, if you look at the top two, which have these weird names, I think that we changed it in the paper, but originally we were just calling them H1s and H4s. We should have called one of them the Chun matroid. I'm still trying to advocate to my colleagues that we need a Chun matroid, but it falls on deaf ears. But so this is a 5-circuit, 1, 2, 3, 4, 5, and it's a triad. And I've circled it because this is a triad in M prime, my minimally 3-connected matroid. How can it be attached on? Well, it could be attached on just like this. That's one possibility. I did not create any 7 cycles. I mean, it was impossible, it's not big enough. It could attach on in this way. It could attach on in this way, where there's an extra edge here in order to get all the way back to this circuit. So it turns out there's only 7 ways it can attach, it can interact with that 5 circuit. And now we use SAGE. So we use SAGE matroids to determine, okay, how can these configurations grow, staying minimally 3 connected without building a larger odd cycle. And we also know, okay, some of these have rank that's too small, so they need to have another triad. And what we end up building is we build these sporadic guys, except we still have to get the book. How does the book arise? Turns out that the book is going to arise from this guy. So I'm going to zoom in on that one. Here I have it's a graph picture that is showing what's happening in my matroid. So when I restrict to the elements 1, 2, 3, 4, 5, X, Y, Z, I really do have a graphic matroid that looks like this. But I'm not trying to say that M prime is graphic. So the way that I build my book from here is you can see that, let me add the dotted lines. Oh, I wish I had this picture. You can see that if I put, I could put one in a triangle with some dotted edges right here. And if I did that, you would see a K4, one being in a triangle with those 2 edges, plus that triad in the middle gives me a K4. So my spine is the 2 dotted edges and 1, that's the spine of my book. And the degree 3 vertices that hang off of it, that would be the circled one. I could add another edge from here to this, between these 2 vertices to get another triad. I could add another edge between here. So this has got within it the startings of a book, and either I will end up building from this configuration one of the other configurations which lead to the sporadic guys, or I end up just, the only way it can grow is by building a book. And that really can happen, and there's no bound you can put on it. But then what you get is a restriction of this binary book. And I like to tell everybody that James Oxley did the SAGE work because he loves SAGE matroids, but I only do that facetiously because it's well known that among the matroid community that he doesn't trust computers. So if you ever meet him, then if you could tell him, I'd really like to see your SAGE work from that odd circuit project. That would really warm my heart. So I'll just end with another slide of the final result. Hopefully that wasn't too technical. Thanks very much.
Thank you so much for the very, very nice talk. Excellent, excellent.
Thank you.
Yeah, if you can, please unmute and clap for Carolyn.
Thank you.
Yeah, so any questions or comments? I have a question related to your major theorem, your classification result about binary matroids containing length 3 and 5 circuits. So what motivates you to pursue this big theorem? Like, if I understand correctly, over a long period, people only get like partial results about that. And you finally managed to complete the classification. So what motivates you to do such a great work?
Are you talking about the splitter theorem for internally four-connected binary matrix, or are you talking about this result for these?
Oh, this one, yeah.
This result?
Yeah.
So Oxley and Wetzler, there's, and this is not true, but I like to think this is true, you know? There's a scene in Lilo and Stitch where the social worker says, I'm the one they call when things go wrong, and things have definitely gone wrong. So I like to say, okay, they got the binary result for the 2-connected case, and then they got the graph result for the 3-connected case, and then they were working on the binary result for the 3-connected case, but had run into an impasse. And I think that also it had to do with Chris Wetzler, with her, she accepted a new job in a different, like she graduated and she had enough for her dissertation. So it's not, they may not have totally needed me, but when I showed up and we were able to complete the project together, it was really satisfying. So it had to do with, I mean, context sort of being everything, because I really was trying to persuade James that we needed to repackage this other result. And he was trying to avoid revisiting that 10-year project. I think he's trying to run out the clock because he may retire before I get him to do it.
Okay, I see. Yeah, that's a great story. Okay. Yeah, if no further questions, maybe we can go to the sharing session. I believe Carolyn has something to say about her experience at the U.S. Naval Academy. Please.
I would love to. And I wanted to ask, are we still recording? We are still recording.
I will stop it right now. Okay.